Okay, so good morning, everybody. I will start by briefly summarizing where we stand yesterday, in particular at the time where I had to go quickly, and then I will take some questions if some of you have from yesterday's lecture, and then we'll go on. So, yesterday I discussed two questions which we want to get answer to. The first question concerns the probability P to find a quark or a set of quarks at location qi at time ti. We ask what is the probability that given that they are at location qi at time ti, what's the probability to find them at another location qf at time tf? Okay? And I argued that this was given by a matrix element of the reduced density matrix evaluated at time tf, matrix elements between the state or initial state of the system and the final state of the system. Remind you that D sub Q is the trace, is defined as a trace of the environment degrees of freedom of the full density matrix of the system. So this relation is valid at all time t. That's the first question. Another related question concerns not the probability itself, but the probability amplitude, which I'm going to call a propagator with a little scribble here, which will make more sense later today. So this is a probability amplitude now to find for the same situation. And that's a propagator which is defined as a sum over n of Pn. And the important point which I want to emphasize here is that the state of the plasma at the initial and final time is supposed to be the same. Whereas in the first quantity here, the probability, we assume that the system goes from one particular location qi to another location qf with the plasma doing whatever it wants to do. The average of the initial state of the plasma and sum over all possible final states of the plasma. Here in this particular calculation, the state of the environment stays the same. This is an important difference which will have impact in the calculation we're going to do. Then I work a little bit on the probability and wrote for this quantity a formula which looks as follows. It's a path integral over a contour of all the paths. So this is an ordinary Feynman path integral, except for the fact that the paths here run along a contour, which is defined as follows. This is the time axis. And the contour goes in the positive time direction from Ti to Tf in the upper branch of the contour. And in the lower branch of the contour, it goes from Tf to Ti. And this contour was introduced to take care of the fact that this probability actually is a square, the modulus square of an amplitude times the complex conjugate amplitude. And these two branches of the contour reflect the time conjugation operation which is involved. And this was written as exponential of S0 of Q, so that will be the free part, just the kinetic energy. And then the effect of the interaction with the environment is entirely captured by what was called by Feynman 60 years ago or so, the influence functional. Why this name? You see here, this path integral depends only on the path, on the trajectories of the quark. There is all reference to the environment, the interaction of the quark with the environment is entirely coded inside this functional. But this functional itself is a functional of the path. Okay? And its explicit expression is given by the following formula. Exponential of I phi is given by, so I'll give you two formulas and perhaps leave it to you as an exercise to show that we are indeed talking about the same thing, A0 of Q and T. So this is the operatorial formula. Remember that when we add the interaction with the medium, the quark interacts only through vector potential, the fourth component of the vector potential, the electrostatic potential, if you wish, or Coulomb interaction. And remember that when I do that, when I add the interaction, it just transforms the kinetic energy into p squared over 2m plus g, the charge, times A0. So this is this quantity here written in interaction representation. I'll say more about that a little bit later, so don't worry too much at this stage. And I have to take the average here, the average over A0. That can be done in several ways. I'm going to assume that the fluctuation of the field are Gaussian. That allows me to apply, in the operator formalism, which is implicit here, to apply Wick's theorem, or in the path integral formalism, that allows me to do the integral, because what do I have to do? I have to do the integral of EJA0 of Q, well, I should perhaps, Q, times exponential of ISB of A0. And if this integral is quadratic in A0, contains derivative or whatever, but if it is of the form A0 squared, then this integration can be done exactly. Okay? And this is what I'm going to assume. Now, I have given, I don't know whether this has been distributed yet, but I have given to Andrea an explicit calculation taken from my notes of this part for electrodynamics. So there you can do explicitly the calculation. There is a fermion determinant which we have to work out and get eventually a Gaussian integral which you can calculate. So all the details are done here. You can do that with Andrea or you can work it out for yourself. It's a simple, I mean, it's not, I mean, if you have never done such things, it takes a little while, but there is nothing very difficult at this stage. Okay, so now a Gaussian integral is, I mean, since this is a Gaussian integral, it's entirely defined by two quantities, which is the expectation value of A0 and the correlator A0 of X, or I should perhaps be a bit more careful, of X and T, A0 of Y and T prime. Or let's say X prime, T prime to be more consistent with the notation. Right? These are the only two quantities which we need. And in fact, I'm going to give a name to this quantity. Not quite this quantity, but a quantity which is the average of the time-ordered expectation value along the contour. And let me spend a couple of minutes to explain to you this notation. But with this notation, I can give an explicit expression for this. This will be g squared over 2 times the integral over the contour of dt1, dt2. Now t1 and t2 are variables along the contour, times this object here, which is a function of t1 Q of T1, T2, Q of T2. Okay? Yeah. So, I am aware of the fact that there is a step here which I'm not going to do explicitly because that will take too much time. But are you comfortable with the steps so far? Or have I lost you? Okay? It's not a big yes, but okay. We'll have various ways to recover these results as we proceed. But at the moment, what I'm doing, I have eliminated. You see, this operation here is a tricky operation. I mean, it's a formal. I mean, when you want to construct an effective field theory, you always want to eliminate degrees of freedom. So this can be done in many ways. In the language of density matrix, this is done by simply tracing the degrees of freedom you don't want. Okay? That's simple to say. That's not easy to do. Now, what I've been doing here with the path integral formalism, and we'll do that by using the density matrix explicitly in the rest of the lecture, is to find a way to integrate the degrees of freedom of the bath. This is the integral over the fluctuation of the field A0. And what I've been saying is that if the action for A0 is a quadratic action, then I can do the integration exactly, and then I get this result, which is exact, modulo the approximation that I've been doing here to get the quadratic form, which for QED is nearly exact, because what I'm neglecting here is essentially nonlinear QED effect, which are tiny. This is light by light scattering, which we start to have control on now, finally, but these are effects which are so tiny that they are very difficult to measure. Okay? So for QED, all what I'm doing here is nearly exact. For QCD, this is another story, which we'll have time to discuss. So let me, there is another thing which I have given to Andrea, and perhaps it has been distributed to you, is the fact that this quantity here will contain several components, which I'm going to list here. So there will be several propagators, and I will, don't know what's happened. I have to stay away from the board. So let me just write the definition, and I will try to make this a little bit more intuitive as we proceed. I'm not writing here the space-time argument. I'm just writing the time argument, because this is the only thing which matters. So there is a set of propagators, delta of t prime, which is given by theta t minus t prime. And there is another one, delta twiddle of tt prime, which I'm not going to say much about. It is essentially, so this propagator here is a standard Fineman propagator. You see, it's time ordered. So if t is bigger than t prime, you take the time order of the two operators, and the time order. You see, if t is bigger than t prime, the time order means that you put the operator with the largest time on the left. So this is this propagator here. This is this component. Okay? And when t is smaller than t prime, you do the reverse. Okay? And that's this component. The reason I'm mentioning this is that you will see this quantity appearing when we work out in more detail what's going on. And besides, these properties have analytic these propagators have analytic properties which play an important role in the discussion to come. So these are very standard. I don't know, is anyone familiar with this type of notation? Yes? Oh, okay. Okay, very good. So at least some of you know about it and can help the others. So, no, it's not on. There is something interface. Oh, okay, okay. Okay, so now, just a remark. This expression here is valid for this probability. Okay? Now, I'm going to leave as an exercise to you to show that the same expression so G bigger, and now you start perhaps to realize there is a correspondence between the notation that I'm using here, which will appear more explicitly later. But this QI is given by the very same functional integral, formally, exponential IS0 of Q, exponential I phi of Q. However, all these objects live on the upper branch of the contour. So, all what I have done with the probability can be repeated almost line by line for the propagator of the heavy quark. But what you will find is that you don't need a contour. You need a contour if you have an amplitude times the complex conjugate amplitude. Here I have just an amplitude. So the same technology can be used as I did here to do the averaging. But since the particle is living on the upper branch of the contour, only the time order propagator will enter. Okay? And this will have a strong impact on the physics. So there are subtleties here which I'm asking you to watch out because, this is somewhat subtle. Not difficult, but a little bit subtle. Okay, so do you have questions at this level? Yes. Yes. This one? Yeah. This is QFTF. On the right is the matrix element. Oh, I'm sorry. Thank you. Thank you. Yes, of course. Of course. Yes.
If you make it forget to
If?
exponentiate.
Yes. Well, it's very hard on the blackboard to realize that this is indeed the exponential. Yes, it is. And I'm not sure about the sign, but it doesn't really matter. Yes. What is phi is this beast here. Or I phi. I will take care of the I a little bit later. I mean, I'm not sure here. But this is exponential. You see, this is it's an explicit expression which gives you, all the information, this is what I was emphasizing yesterday, all the information we need about the plasma is contained in this correlator. So if you know this function, it's a function of 4 times 4 variables. If you know this function, you know everything you need to know about the plasma. So you don't need to know the detail of the interaction. You just need to be able to calculate this. And we are going to calculate this in some particular circumstances. This can be calculated non-perturbatively if the plasma is strongly coupled. You can calculate it on the lattice or by by your favorite tools. But you don't need to go deeper into the details of the dynamics of the plasma. Okay, is there other question or mistake to be corrected on the board? No. Okay. So this I have done a calculation here where I have departed from this formula. I have abandoned somehow the density matrix for a moment. showing you that we can arrive at what we want by using functional integral techniques. And what I want to do now is to return to the density matrix because, first of all, it's good to have some familiarity with both languages. And it turns out for QED, we can go quite a long way with path integral. For QCD, there are subtleties which are easier to handle with the density matrix and with path integrals because of the non-commutation of the color matrices. That complicates a little bit the game. So let me return to density matrix. And what I want to show you is to how we can derive approximate equation for the density matrix. So back to the density matrix. So I will what I will do is to write down equation of motion for the density matrix, show to you how we can solve this equation using perturbation theory, and then indicate how we can easily go beyond perturbation theory in order to recover a formula which is somewhat like this one. It will not be exactly the same formula, but will have essentially the same physical content. So I'm going to set again the Hamiltonian as HQ plus HB plus H1. This I'm going to rewrite as H0 plus H1, treating H0 as a free Hamiltonian and H1 as the interaction. Okay, so I'm going to do the standard perturbative analysis. So associated to H0, there is an evolution operator from T0 to T, which is exponential minus I H0 T minus T0, correct? And I am also going to assume that at time T, well, no, I'm not going to assume. The density matrix associated to this evolution operator, which I call D0 of T, is obviously the product. Because you see, with this kind of Hamiltonian, which is a sum of Hamiltonian which involve different degrees of freedom, the Hilbert space is a sum is a tensor product of the Hilbert space associated with the quark and the bass, and the density matrix is also has also this form. Okay, so it's factorized, which is indeed easier to handle. Then I go, as we do in perturbation theory, I go to the interaction representation in order to eliminate the trivial time dependence coming from H0 and focus on the interaction piece. So I write U of T and T0 equal to U0 of T, T0 times interaction U sub I of T and T0. And I define also H1 interaction of T is U0 dagger T0 H1 U of T and T0. Then it's not, then I can rewrite equation of motion. Remember that U satisfy essentially the equivalent of the Schrödinger equation, and U0 satisfies the Schrödinger equation for the Hamiltonian H0, and the equation satisfied by U sub I is d by dt. I d by dt is of U sub I. So I'm not doing the calculation explicitly here, but takes two lines, and I'm sure you all have done it, is equal T times U interaction T0, with of course a boundary condition that U sub I of T0 T0 is equal to 1. And the solution of this equation can be written as a formal time order exponential. This is time order exponential of minus 1 over, yeah, I did not put the h bar here. Maybe I should do that for a little while. I h bar of the integral from t0 to t okay. So what I was referring here to the averaging operation, it's an average of operator like this one in the interaction representation. Okay, but let's not digress too much at this point. What I want to do is now write down an equation of motion for the density matrix in the interaction representation. So I'm going to define, to extract from d of t the trivial time dependence defining the interaction representation of d. I have to put the dagger in the right place. And of course, d of t0 is equal to d0 to d of t0, because at t equal to 0, these operators are just unity. Okay? And then you can show that d sub I by dt is given by the following equation, hi 1 of t d sub I of t. And if I want to have the equation for the reduced density matrix, well, all I have to do is to take the trace of a b of h1 di of t. Now, on the left-hand side, taking the trace is easy because by definition, this is the object I want. This is a reduced density matrix. On the right-hand side, part of the difficulty now that we have to face is how do we calculate the trace and get a closed equation for d sub q. Here, this is a full density matrix which appears. Okay? Okay, so this is where I will go into perturbation theory, and the purpose will be twofold. One is to familiarize yourself with the type of diagram which you have to deal with in this particular context, which will involve the Schwinger-Keldysh contour again, and perhaps make contact with what we have been discussing earlier. But you have questions on this part of the, I mean, this is pretty standard, but no. Okay, I mean, everything is done. I mean, almost. So perturbation theory. Well, perturbation theory is actually already coded here. You see this expression written of the evolution operator, written as the t product of, the t exponential, involve the interaction. So this interaction is proportional, let's say, to the coupling constant. It's essentially g times a0. So this exponential can be expanded in power series in powers of g. If I do that, I can write for the density matrix a corresponding expansion. And let me do that. So, let's see, how do I do that simply? perhaps I should remind you, yeah, let me remind you a formula which we had written yesterday. Remember that yesterday we wrote an equation. Let me try to put the sign correct. So let me recover the exact equation. Oops. Well, I don't have it here. Yesterday we wrote, and you will correct me if I make a mistake, we wrote an equation for D, which was just a commutator of H with D of T. That's the exact equation, all right? And I claim that the solution of this equation is of the following form. D of T is D of T0 and multiplied by the evolution operator on the left and the emission conjugate on the right. Okay? I mean, a simple mnemonic to remember that is to view the density matrix as a projector on a quantum state, if it is a pure state, and then to calculate, to go from psi at t0 to psi at time t, you have to multiply by the evolution operator on the left and by a complex conjugate on the right. Okay? So that's the way to remember. Okay? So now I have essentially, I mean, you should not have too much difficulty to accept the fact that for this equation here, the solution can be written as di of t equal u sub I of t and t0 di of t0 times u sub I of t and t0 dagger. Okay, so it's the same formal equation. I put the subscript or superscript I everywhere. That's it. You can verify it. If I take the derivative of this equation with respect to t, I recover this equation here, right? And then, so you see, to calculate d sub I in perturbation theory, I have to expand this evolution operator using this formula here. Okay, so it's the same kind of strategy as I used for the using the path integral technique. I will have ordered operator on one. I mean, I'm going to use the Schwinger-Keldysh contour. I will have one set of operators which will be ordered along the upper branch of the contour corresponding to u sub I. And then I will have another set of operators which will be ordered in the reverse order corresponding to u dagger. In other words, what I'm going to do is to draw the contour like this, going from, now I'm going from t0 to t. Okay, so I will have the density matrix at time t0, and to calculate the density matrix at time t, well, this is all in interaction representation. I have to expand the evolution operator u sub I of t and t0 here, and expand the operator u I dagger of t and t0. Is that clear for everybody? Yes? I'm doing all the steps now, so you should be able to follow me. I need another board. I would like to keep, well, I can erase this. So how does the expansion of this operator looks like? So I mean, let me redraw. Now I'm going to draw diagrams. It's a little bit easier to visualize than the formal expression. So remember that H sub I is just what's written over there, G times A0. Okay. So if I imagine that this is a trajectory of the quark, it doesn't need to be, but this will be. I'm going to draw a little line here to indicate that in first order, the evolution operator will contain the free up to some time t prime, where the particle will interact with the field A0 at that particular location, and then continues from t prime as a free propagator. That's the meaning of the expansion here. See, what I'm saying here is that in leading order, u of t and t0 is equal to 1. Let me drop the h bar. And so that will be 1 plus I, the integral from t0 to t, dt prime of hi of t prime. But hi of t prime, this is what? This is u dagger 0 of t prime and t0, h1 u of t prime and t0. So this h1 here is g times a0. So at some particular t prime, I mean, this is h1 now doesn't depend on time, but this is measured at time t prime. And what I'm saying here is that I go from t0 to t prime without interacting. Then I have an interaction, g times a0, and then I go from yes, there is a subtlety here. And then, in fact, this other evolution operator contains this piece here, which I have not considered so far. Let me. I'm sorry. This is correct. I was just trying to find. No, this expression is correct, right? This is just copied from upstairs. So we have to. I mean, there is a subtle point here, which I don't want to insist too much on, because there are other subtleties which I want to indicate. This operator here is just acting. Is just part of what is going on here. The integration of a t prime indicates simply that the interaction can take place anywhere once between t0 and t. That's this integration here. And then this is just the interaction representation where you eliminate the free propagation between t0 and t prime only. You don't care about what happened here because this cancels out. This is essentially what's going on. So, okay, let me, I mean, I stopped, perhaps I should not have stopped, but I think this is clear that this is the leading order, this is one of the leading order conditions. Now, this involves the expansion of this part of the evolution operator, but you have now the other part of the contour, which is here, where you will have another diagram in which you have, so this is T0 and T, where the interaction will take place on the other operator. Okay? That is a complex conjugate. One has to be careful because the diagrams are drawn in the interaction representation. And what I was doing here is somehow undoing the interaction representation, which I should not do. But I hope I did not introduce confusion, too much confusion. Is that clear? Okay. So now I want to do to second order. So this is first order. That will be just a complex conjugate of this. Second order. So second order, I will get minus a half T0 to T dt prime, and I will get H1 at time dt prime, dt double prime. I will get an H1 of T prime and H1 of T double prime. In fact, there is no need to put, I can put that here, and there will be time ordered, but this is time ordered along the contour, okay, according to what I have discussed. Well, let's. I'm sorry. Let's not drop. This is expansion of u sub I. So this is a time order. This is a usual time order. So let me draw the corresponding diagram. So this is T0. This is T, and then I have the possibility. To interact twice with the field at time T prime and time T double prime, A0. A0. Okay? And that will be the time-ordered propagator, right, as it comes from the expansion here. So that will be the usual Fineman propagator for this particular case. Okay? So here, this will involve Fineman ordered propagator. Then I have another set of diagrams where the two field A0 are attached to the line below. And you can verify for yourself. I need some room. I guess I can erase this. Okay. This is just a preparation for equation. Then I have this type of diagram. This is T0, this is T. And this type of diagrams will involve anti-time ordered, and that's a propagator which I have called delta tilde of T prime. Namely, this is the same as a time ordered, except that the ordering of operators is just opposite to that of the time order. Time order means that you put the bigger time on the left, and the lower time on the right. Anti-time order, you put the bigger time on the right and the lower time on the left. Okay, but this is the same thing. And then there are two other diagrams which are interesting, T0 and T, which are diagrams in which you have one A0 upstairs and one A0 downstairs. And this involves now these these propagators, D bigger. This will involve, not yet, this would involve these propagators which are written upstairs here. In fact, the propagators will come will come at the next step, which I haven't done yet. This is just the propagation in an external background field, A0. Okay? And what I have done so far is just expressed everything in terms of the time-ordered exponential. And for this particular here, I have anticipated a bit I'm sorry, I have anticipated a bit by mentioning time order. This will come now, okay? It's not wrong, but it's a bit, I should have said that a little bit later, okay? So is that clear what I'm doing? I mean, I'm just doing second order perturbations here. Yes?
So I can get the second order, and why there is not in the second order the propagation with the U0 evolution operator, like in the first order? So why don't we have the integral from t0 to t, dt prime, dt second, with then u0?
Oh, because I have not done here. Here, I'm not sure I understand your question. Here the u is u0, yes. But all this quantity here is h1i of t. Okay, this is the interaction representation of h1, which I have opened up, which I may have skipped that, because that probably introduced a little bit of confusion. But here I have not done that. I just stick to the interaction representation and forget about the specific meaning of that, okay? Because I realize by discussing it that it's probably introduced some confusion to do that. It's not wrong, but I don't need it, okay? So here I have two integration, and there is an implicit time ordered, because this is what perturbation theory tells me, okay? The propagator are going to come soon, but the only thing is that the word propagator is a little bit premature. But this is a time ordering of the sequence of interaction. Okay, that clear to everybody? Okay, so now we are going to do the. So far, I have described the effect of the interaction using standard perturbation theory. And now I want to do one thing, which is I have erased an important equation. Yes. Well, the equation I need is still here. That is d sub I of t is equal to u I of t0 d I of t0 u dagger of t0 all in the interaction representation. This is the equation I want. So what I want to do now, remember, what I am interested in is the reduced density matrix. So that means that I have to take a trace over B of the whole thing here. Okay? In principle, this is hard. However, in the particular context here, remember that di yes, I am going to assume that the d at time t0 factorizes, let me erase this, at time t0, d of t0 is a product of dq of t0, I already mentioned that yesterday, times d bass of t0. And I'm going to assume a thermal bass. So this is a standard thermal density matrix, e to the minus beta h, bass. And given this, then I can easily perform the trace over the Bass degree of freedom because of this factorization. And I can do that explicitly, but before doing that explicitly, I am going to do that diagrammatically. So you see, if I do the trace, you see the only thing which will contain A0 is coming from the expansion of the evolution operator here. Okay? So all the information of A0, about A0 is contained in these diagrams. So when I do the trace over the Bass degree of freedom, that means simply that I average A0. So the operation that I'm going to do here is just to replace in first order A0 by expectation value of A0. And in fact, in an ordinary system, the average of the gauge field is 0. I mean, we are considering control systems. It will be true also in QCD. We are considering the plasma as electrically neutral or color neutral. The expectation value of the field is 0. The only thing which will play an important role are the fluctuation of the field. The fact that expectation value is 0, but the field will have the product of field will have expectation value. So here, you see, I have to do the same thing. I'm going to take expectation. Okay? But what is this expectation value? It will be a propagator, which means that this diagram, after the averaging, I can rewrite in the following way. This is T0, this is T, and this is a diagram which is essentially a self-energy contribution on the upper line. So this particular diagram, this particular averaging, tells you that the quark propagates in the fluctuating field, and because of that, it acquires a self-energy, modification of its mass, and some more subtle effects that we will discuss in the second lecture today. Okay? And now I have the same, obviously, for the lower part of the diagram, so we'll have another self-energy correction on the lower line. And then I have these two diagrams here, which I have to redraw now. And this is where this propagator will enter. And you will see that this diagram plays an important role in providing imaginary path to potential between heavy quarks. So I have one diagram like this. I mean, these diagrams will contribute one of these, which can be either one of these two objects here. Let's say delta bigger or delta lower. These two quantities are related by simple permutation of the time arguments. Okay? So this is second-order perturbation theory, and perhaps I should write down, or perhaps not. I think it's a good point to stop. I'm not going to write down explicitly, we can do that, write down explicitly the equation corresponding to these diagrams, but I'll do it when I need it. Okay, so at that time I will stop, and if you have questions, we can stop, let's say 10 minutes. I'm sorry? 10?
Just a coffee.
Just a coffee, okay. So 10 minutes, so we resume at 10:05, okay? And there is a second commutator, which is given by this expression. Okay, so this is not a difficult exercise, but I invite you to do it. At least forces you to really understand what has been going on here. The trace has been done. You see, this is a closed equation for the reduced density matrix, and all the information about the plasma is contained in these two correlators here. Okay. So try to work it out. I mean, it's not hard, but if you succeed, that means that you have understood most of what I wanted to tell you today. I mean, in the first lecture. Then in the second lecture, we are going to make use of all this in order and introduce some more physics and discuss what happened for two particles, because eventually we want to discuss the physics of quarkonia. And yeah, there were some typos in the formula which were written on the board, which I've just erased, I'm sorry. But if you find, I mean, be aware of the fact that some letters were missing on H1 or HI. So don't be surprised when you read your notes if that's happened. So what I want to do is to calculate the two-particle correlator, make contact with what is calculated on lattice, which is a free energy that will take me to consider the time as a complex variable. And finally, I want to discuss the complex potential, which, as I will discuss, reflect the effect of the collision. So now we have two particles. So the kind of diagrams which I was drawing before have to be made a bit complicated. I will have quark, anti-quark. Quarks and the anti-quarks are non-relativistic particles, so I don't make any distinction in the arrows. They go from, let's say, from T0 to T. So I will have, I will have diagram like this, self-energy, and important diagrams which will connect upper and lower branches of the Schwinger-Keldysh contour. Okay? So now the contour is a little bit more complicated because I have two particles moving in one direction and two particles moving in the opposite direction in the lower branch. One is a quark, the other an anti-quark. And I'm going to write for the correlator the following expression. So for the moment, for the first part of the lecture, I'm going to ignore the second branch and focus on the correlator, which involves two particles propagating on the upper branch of the contour. And that correlator, I'll write it in the following way. R2 bar. It's a function, so this is a T, and R1 bar at T0. So in other words, the diagram which I'm considering now is the following. I have a quark at the time T0. At T1, I put a bar on the coordinate of the anti-quark, and this propagates from R1 to R2, and the anti-quark propagates from R1 bar to R2 bar. And for a reason that will be perhaps apparent later, I'm going to use now to use a second quantized formalism to describe the quark and the anti-quark. So this propagator is the amplitude for the following process. I create at time T0 a quark at position R1. I create an anti-quark, so I put a bar, but the bar doesn't have the meaning of a Dirac bar. It's not psi, dagger, gamma 0. It's just the creation operator for the anti-quark. Okay? So it's just like the psi dagger at T0 and R1 bar. And then I destroy the two objects at time T. Psi of time T and R2. Okay? So this is the object which I want to evaluate. And it's convenient to do so, to introduce currents, the analog of what I did before. But now this would be a function of T, R, and R bar. And by definition, this is psi, this contains a distraction operator, psi of T and R. Okay. Yes, and GQ dagger of T or R bar will be the same thing now with psi dagger of T and R, psi dagger, psi bar dagger of T and R bar. Okay? So these are the operators which create a pair of quark anti-quark at at a given location. I'm going to use quarks, even though I'm not going to worry about color today. So you can think of this as just electrically charged particle with plus and minus charges. But I will use the language of QCD for this. And these operators are just evolving in time in the Heisenberg representation. So this is exponential IHT of GQ of R bar exponential minus IHT. Okay? Usual standard 6. Okay. So now I want to see what kind of information is contained in this object. And I remind you that the Hamiltonian is still the same object as before, where now H1 will couple to this current JQ. So that will be the form JQ times A0. And then I will assume that the density matrix of the bass is of the form exponential minus H over the partition function of the bass. Okay, a thermal average. So if this is the case, I can calculate the propagator G bar, which is sitting upstairs here, and let me drop all the coordinates. That's the reason why I'm introducing this notation. The coordinates will not play much of a role in the discussion to come. I will just focus on the time variable. This is on the time that I'm going to work. So you can, for yourself, if you wish, keep tracks of all the variables, but I'm not going to do that. And then I write this expectation value. I do the trace of the Bass degree of freedom, sum over n exponential minus beta En, sum over m. And now, yes, perhaps I should do that in step. So this is n, and then I have to take the expectation value of JQ of T, JQ dagger of T0. Okay? So if you look at the correlator here, you see the first collection of term is just a JQ, and the second one is JQ dagger at T0. Okay? And now I remember that the time dependence is given by this expression here. And this can be rewritten as sum over n e to the minus beta En, n. And then I will insert a complete set of state here, GQ n. And then I have to take care of the phases. So the phases here will be exponential let's see, I E n t minus, well, let's say this is t, so this is I n t exponential minus I e m t, and then I have the same thing with t0, so I just write this minus t0. Okay? There is a sum over m, which I have, yes, omitted here. Now, what I'm doing here, I'm summing of the state of the plasma, the state m, the state m, the state n. The plasma doesn't contain any heavy quark, and then I have here states which contain, in addition, well, I'm sorry, I forget the dagger. In addition, the state m will contain a pair of the heavy quarks. Okay, so this now I can rewrite explicitly as a 1 over z, sum over n. Well, I mean, I think I don't need to rewrite too many things. Now, this what I want to argue now is that this is a function which is perhaps I can get rid of t0. Let me take t0 equal to 0. Then this phase is e to the en minus emt. That simplifies a little bit the discussion and doesn't do too much. Now, what I want to argue is that, you see, I mean, I want to let t become a complex number. And you see, this is a sum of exponential terms which are cut down by this exponential factor. And as long as it remains smaller than beta, the sum here will guarantee the convergence. I mean, in most situations. I mean, you can perhaps imagine a situation where, because the density of the states En follows this and this property, the sum doesn't converge. But in general, if I let t become complex, and it smaller than the beta, then this function will be, this sum will be convergence. In other words, g bigger of t is an analytic function in the strip minus beta, imaginary part of t smaller than 0. And in particular, for t in the boundary of this regime, for t equal minus I beta, I can calculate this expression and get the following. G bigger of minus I beta is equal to, well, if t is minus I beta, this factor cancels this one. And you see I have exponential minus beta em times the sum of m. That is just the partition function. It will be just reconstructing, I'm sorry, the density matrix, the thermal density matrix. In other words, this is just 1 over z, the partition function, the trace of gq exponential minus beta h gq dagger. Okay, this is an important formula. I'll come back to it a little bit later. Okay? Okay, now I need to make a couple of remarks on the propagators, which perhaps I will skip now and go directly to the discussion of this formula. Okay, is this clear what I've done? I mean, it's just simple algebra. Okay, and the only difficult part here is to realize that there is a factor, exponential factor, which will control the convergence of the sum, provided, and when t becomes complex, provided the imaginary part of t doesn't get too big. Okay? And I'm going to assume this is the case. And in the particular situation where t is exactly equal to minus I beta, then I obtain a simple formula. And I want to give you a physical interpretation of that formula. Sure.
So, when we took the ensemble average, was it for the full system with the full Hamiltonian, or was it for only the bus?
Well, it's a full Hamiltonian, but you see, I'm going to comment on this. This is a full Hamiltonian, but you see, the trace here, the sum over n, there is no heavy quark in the state n do not contain any heavy quark. So these are eigenstates of the Bass Hamiltonian, because there is no heavy quark, so there is no interaction and between the heavy quark and the plasma, and therefore the state n can be considered as eigenstate of the full Hamiltonian. Okay? Because these are eigenstates of the Bass Hamiltonian, but the states in question do not contain the heavy quark. Okay, by assumption. The state n here do not. The state m now do contain the heavy quark, but I haven't said too much about that yet. Okay? And in fact, you see, this is beta h, a full Hamiltonian. I have to say more, which I'm going to do now. Okay? So, what is this object? Yes, so I've just commented on the fact that the state n can be chosen to be the eigenstate of the Bass because there is no heavy quark in the Bass, so no interaction whatsoever. Let's see, yes. So, one thing I have not, which I have not done carefully, I've left completely aside the coordinate. So let me, for the time being, assume that m goes to infinity, then the dependence on the coordinates that can be shown explicitly will just generate delta function of the location, R1 minus R2, delta of R2 minus, of R1 bar minus R2 bar. What I'm saying is that physically, if the quarks are infinitely heavy, they don't move. So they remain at the location they started from. Okay? So that's taking care of the coordinates. And then I can always write as a basis for the full eigenstate, I can always write as a basis the product of state of the plasma times the state of the two heavy quarks. In other words, the state JQ dagger acting on M, they are product states which constitute a basis for the on which I can expand all the states on the interacting system. And then the expectation values that I have to calculate is of the following form: 1 over z times the sum over n j e to the minus beta h dq dagger n. Okay? What I'm saying is that this constitutes a basis of states for the interacting system. Of course, in the presence of interaction, the states will be mixed with one another. They are not going to remain product states. They are product states only if I ignore the interaction between the heavy quark and the plasma. But they constitute a basis. Okay? So what is this sum here? You see, this sum is just the partition function for a system in which I have two heavy quark, one anti-quark, on top of the plasma. So this sum over n here is a partition function for two heavy quark plus the plasma. And what is Z? This is Z. This Z here, remember where it comes from. The Z was coming from the sum over n here, but the sum over n where really is a state of the plasma. Okay, as I argued before. So this Z should be a Z sub B. So this is a partition function of the plasma without the heavy quark. Okay, now the partition function Z is exponential minus the free energy divided by the temperature. That's a standard thermodynamic, right? This is free energy. Internal energy minus T times the entropy. Therefore, this quantity here is what? This is exponential minus the free energy of the QQ bar system over T times exponential of plus, because it's in the denominator, the free energy of a bath divided by T. So this is equal to exponential minus the difference of free energy of the system with two heavy quark present minus the free energy of the system without the heavy quark. Okay? So we have obtained this formula here, that this quantity is minus delta, exponential delta F QQ bar over T. So you see, by calculating this correlator in imaginary time, with a time equal to minus I beta, I get access to the difference of free energy between two heavy quark in the presence of the plasma and with respect to the free energy of the plasma itself. This can be now evaluated on the lattice because I'm doing now imaginary time. So there is no difficulty to evaluate this on the lattice, and in fact this has been done for years and in a different context. And I just want to give you another exercise that which you can also do and should be instructive given what we have done so far. Let me erase this. So prove that G bigger of minus I beta is can be written as the expectation value. The expectation value is over the states of plasma of exponential Ig times the integral from 0 to beta d tau prime. Now this is imaginary time. The A0 is moved into Euclidean representation, so it's tau and r, 1, let's say, exponential minus ig of 0 to beta d tau prime, a 0, the E stands for Euclidean, tau prime r2. You can set R1 equal to R2. So this is usually called a Polyakov line. The I here is due to the change of, I mean, there are two I's actually, that's why one remains. When I change time into imaginary time, there is an I in the time, but when I go, you see, A0 is like a time derivative, so when I go to Euclidean, there is another I coming up. So the net result is this product here. This is not the same plus I minus I that we were dealing with when we were calculating amplitude and complex conjugate amplitude. Here we are talking about an amplitude. So this minus I here refers to the fact that there is a quark with plus G and another anti-quark with minus G. So this is instructive exercise to try to do that. It's not difficult. This is the same kind of averaging that we have done several times so far. I mean, averaging this over A0 using, well, this can be done in either using the density matrix argument that I've been using here, or using a Gaussian integral, if you wish. Well, actually, this is a... actually, I don't even think that the Gaussian answer is necessary for that, but you can think about it. I mean, that's... Okay, so this is the first thing I wanted to do, to show you that in this particular, for this particular correlator, which I have discussed previously for the case of one particle, now I have two, that correlator in imaginary time provides information about the free energy of the system, or rather the difference in free energy of the system with and without the heavy quark. Now, I would like to proceed further and calculate the influence functional that corresponds to this propagator. So it's going to be the same formula as we had before. Namely, I'm going to write G bigger as a function of, let's say, let me call capital XF collectively the two coordinates R1, R2, or R1, R1 bar, let's say, of the quark and the anti-quark, just to save a little bit of writing. And that, according to what we discussed previously, that's going to be a path integral over, which I denote symbolically by x. Now there are two passes, one for the quark and another one for the anti-quark. Exponential I times S0 of x, that's a free propagation. And then I have exponential I phi of x. And now phi of x will be given by a formula very similar to the one we have already discussed. That will be given by an integral from Ti to Tf dtx, an integral Ti to Tf dy, the integral d3x, integral d3y. So this is a full parametrization of the path. There will be a density, txx, our famous contour propagator, tx minus ty, x minus y. I mean, it depends only on relative coordinates, both in time and space, simply because I'm assuming that the plasma is uniform and translationally invariant, both in space and time. The Hamiltonian of the plasma doesn't depend on time. Then there is a rho of ty, y. So rho of x here is what? Rho of x is simply g times delta x minus, how do you want to write it?
Please, you should mic a little forward. Yeah.
Yeah, can I do that? Let's do the experiment. Yeah. Good. Okay. Delta of x minus r bar minus g delta of x minus r bar hat, where the hat here denotes the position operator, as we did for a single quark. Okay? So now you see it's the same structure. So I haven't done anything, but there is nothing to do. The only complication here is the bookkeeping. We have to take care of the fact that we have one quark, one anti-quark. So there will be components of the density. You see the density has two terms. So there will be two terms here, two terms here. There will be four terms with plus and minus signs. So I can, and all these terms now will involve propagators which are living on the upper branch of the Schwinger-Keldy. So there will be time order, regular propagator. Okay? So, so let me give you one example. You can calculate then phi for QQ bar. Let me give you the result for QQ bar as a function of x. This is minus g squared. The minus comes from the fact that I have two opposite charges. The integral dtx from ti to tf, the integral from ti to tf dty, and then I have the propagator tx minus ty and r of tx minus r bar of ty. So you see very much the same formula as we had before. This is this is a regular, usual Feynman path integral, but you see there is a subtle, a strong correlation between the points and the paths. The paths are not simply random walks as they are for a free propagator. They are random walks, but they are correlated. Different points along the path depend on the state of the medium. So this function here tells you, it contains in particular the fact that when you put a heavy quark somewhere, it will polarize the plasma in its vicinity, and when it moves, this polarization cloud will follow or do something else. So this is the type of correlation that we have to deal with. And this is what brings me to the last part of the lecture. I want now to analyze this propagator a little bit further. And to do that, I need, yes, this. Okay, so this is what I want. And I'm going to do the analysis in the case of the very massive quarks. Nothing very profound changes when the quark mass is not infinite, but for the discussion of the board, it's better to get rid of this additional complication. So I'm going to take the mass going to infinity. Then, as I argued before, when the mass is very big, the quark don't move, so this will remain a constant. which I can choose equal to 0. Well, no, it's a constant. So the phi QQ bar will be minus g squared, the integral dtx dt. Then I have delta let's see, I'm missing something, I'm sorry. X and Y. That seems to be correct. I'm missing a term. I'm sorry. I am missing a term which I don't find on the board. Tx minus Ty, R of Tx minus R bar of Ty. The term which I'm missing, I may have forgotten something, is a term of this form, Tx minus Ty and 0. I'm sorry, yes? Yes? Capital X means essentially R bar, right? Okay. QQ bar. Perhaps. I'm sorry. I am missing one term right now. There is. I need this term, but I don't think. Okay, let's proceed. I apologize. I've left something on the way. I think this is correct, though. So what I want to do now, and let's continue a little bit, and perhaps I will find out what I'm missing. So I do a Fourier transform of this expression, d omega over 2 pi, e to the minus I omega tx minus ty times delta of omega r minus r bar. And I Yeah. There are two terms, and presumably, yeah. Okay, I think you're right. I think you're right. I'm missing a term. Yeah. There is a question mark here. It's nothing deep, nothing deep. But okay, let me continue, because I would like to arrive to an important result. So I guess this expression is correct. So I take the Fourier transform, and then I use the following formula integral dtx dt exponential minus I omega tx minus ty. This is a standard type of things in the time-dependent perturbation theory. 1 minus cosine omega tf minus ti. Okay. And then I am going to argue that I am interested in time tf, or tf. So this is integral ti to tf. Tf minus ti, which are big compared to 1 over omega. In other words, I am interested in omega will be characteristic of the plasma response. And I am interested in the motion of heavy quark on time scales which are, I will come back to this discussion, on time scale which are large compared to the typical time associated with plasma response. In other words, I am looking at I'm going to make an approximation where I shall assume that the plasma responds essentially instantaneously to the motion of the heavy quark. This is, of course, an approximation that we shall have to correct by additional terms later. But at the moment, I am just looking after the leading order term. So in this situation here, this expression 1 minus cosine omega t when t goes to infinity divided by omega squared, this is equivalent to 2 pi times t times delta of omega. In other words, here in this particular situation, this correlator, you see, this influence functional will be proportional to t. Now, remember, it is in a path integral. It's proportional to t. It's almost like you had a potential term. And besides, that potential term will be given by the static part of the plasma response. So let me try to put that into a better shape. So, in other words, what I want to do now is to introduce the complex potential. So what I have argued is that this functional integral phi q bar is minus g squared, while there is a 2 pi t delta of omega, so that will give me a delta of 0 for omega equal to 0 at the location r minus r bar minus delta omega equal to 0 and at 0 separation. I mean, basically, as you will see, this is interaction term, and this is something which corrects for self-energy of the particle. So now I need to evaluate delta of 0. And in view of the time, I'm just going to give you the result. This is an exercise that is not too hard to do, but I'll just leave it aside for the time being and give you the result. Remember, this is a time-ordered propagator, and delta of omega can be written quite generally in the form of a retarded propagator for omega plus I times delta smaller of omega. These are these beasts which are on the board here, the Fourier transform, which I did not have time to discuss in great detail. And it turns out that for omega equal to 0, delta, the retarded part of the propagator, is real and can be associated with a real part of the potential. Let me put an R here. Real part of the potential, real. And this correlator delta smaller of omega and R is actually also real, but it comes with an I here, and that is going to be called W of R. And that's complex, that's the imaginary potential. Imaginary potential. So, by calculating this influence functional, you see that I can rewrite this object here as minus 2 pi t times g squared times the delta, there are minus sign, I'm sorry, there is also minus sign, times V of R plus I W of R. And I want just to finish by giving you the shape of W of R and make a set of comments on it. Let's see, I want to keep that here. So W of R can be calculated in a hot thermal loop approximation that I already mentioned. In the context of thermal field theory, this is just a one-loop calculation with some approximation, some kinematical approximation. And what we find is that what we find, well, both can be calculated, V of R and W of R. One finds that V of R is equal to G squared over 4 pi times the Debye mass plus or minus G squared over 4 pi, that's alpha strong, minus M Debye times R over R. So this is a screen Coulomb potential. So that's one of the effects of the plasma on the heavy quark motion, to generate a correction to the potential which is induced by the screening effect. Okay? And W of R can be expressed in terms of the following function, G squared T over 4 pi times a dimensionless function, which I will call phi, little phi of M Debye times R. M Debye times R is dimensionless. And let me write this function here. This is a function which starts at 0 quadratically and goes to a value which is 1 or 2 depending on the, let's say 1 at large distance. And this is as a function of R. This is R of the order of the inverse of the Debye mass. The transition region is characterized by the scale M Debye. Now, what is the physics going on here? The physics which is involved in the potential is the physics of collision. Is the fact that the heavy quark propagates. So there are two heavy quarks. Okay, let me draw this here. There are two heavy quarks. They propagate, and they propagate in a plasma where they can collide with other particles. So this is the heavy quark. This is a heavy quark, the anti-quark. So there are a set of insertions. This is like the insertion of A0, but the A0 is produced by a particle in the medium, and I have others here. And there are several ways to look at the same thing. If I now do the averaging of the medium, what do I get? I get diagram in which we have, I will close this line and reconstruct a little fermionic bubble here, which when I cut, give me the imaginary part that I'm calculating. But it's better to keep this as an effect of collision and try to understand what is going on here. So there are two types of processes. When the distance between the two heavy quarks is large compared to the inverse of the Debye mass, the two quarks essentially ignore each other. And what we see as imaginary part is just the fact that because the heavy quark collides with particles, if you ask what's the probability to find the quark in a given momentum state, that will change rapidly in time because the quark will be able to accumulate momentum because of the collision with the light particle. So there is an imaginary part in the potential for even one single quark, which is usually referred to the damping, to the heavy quark damping. And there have been a lot of confusion in the literature because people have been solving Schrödinger equation for this propagator. You see, the exponential time times the potential suggests that the dynamic is that of the Schrödinger equation for a complex potential. And of course, if you solve a Schrödinger equation with imaginary potential, you find that the norm of the wave function decreases. And then the people started to worry, where is the heavy quark going? The heavy quark is there. When the heavy quark collide, the heavy quark after the collision is still there. What is changing? What is changing is that the state of the heavy quark before the collision is not the same as the state of the quark after the collision. And this is precisely this information of the state of the heavy quark that is measured by this correlator. So you have to be careful about, there is a Schrödinger equation underlying the physics here, but that Schrödinger equation is not for the state of the system, it's for the propagator. And it's the same, it's a self-energy effect, is the fact that when the heavy quark propagate, it can move to another more complicated state, like a gluon or a photon. And if you want to analyze the probability to find the heavy quark in a pure heavy quark state, you will find that it is smaller than 1 because it is mixed with more complicated Fock states. So that's the physics of what's going on here. So what's going on? Why does it go to 0 when the distance becomes small? That you should be able to guess physically. So I'm talking about the two heavy quarks propagating. So they are interacting. They are attracted, even though the potential is screened. However, when they are close together, the effect of the collision doesn't seem to matter.
So the medium cannot resolve.
Yes, this is essentially what happens here. You see, in this region, in terms of the diagram which I was drawing before, we have this kind of processes. In this region, we have interference diagram of this kind, namely interaction between the quark and the anti-quark, and there is a cancellation between this and this, and that cancellation reflects the fact, this is a generic property of gauge theories, reflects the fact that when the quark and anti-quark are close together, they form a color or a dipole, a small dipole. A small dipole that is electric. I mean, it's a neutral object, and if the size is small compared to the typical wavelengths of the mode of the plasma, there is no chance that the plasma can see the individual charges. It will see only the dipole, and the dipole is not visible for gauge potential because it's a neutral object. Okay, so this is what happens. So you see, the collision manifests themselves in a subtle way. I mean, they produce a damping, so-called damping of the heavy quark. That is to say, there is a change in the state of the heavy quark due to collision. However, when the two quarks are very close together, this effect disappears because simply the system becomes neutral. So this is the important physics contained in this complex potential. We will come back on this in the next lecture. We'll perhaps give you more details or perhaps try to work out a couple of exercises for you to fill in the gaps. But basically, the same thing will happen for QCD. I mean, I've not discussed QCD so far, but it will be the same. Okay, sorry for too much time, but thank you for today.